So in the previous videos we've been looking at how we would measure the push or the pull, the amount of movement of electrons that each half cell might be able to contribute towards an entire cell. So we've been measuring things against the standard hydrogen electrode, and we've been getting values, and some of those numbers have been positive and some of them have been negative. Remember that we're showing everything as a reduction in this series, despite the fact that it might end up being an oxidation. These are all written for consistency in the same way, and we're looking at their ability to push or pull electrons around this circuit. So we measured a few, and we talked about how to measure them, measuring them against hydrogen. And remember that the standard hydrogen electrode by definition had the value of 0, and it's on this little thing, it's here. This is called an electrochemical series. So an electrochemical series puts the half cells in order from those that will want to undergo reduction the most at the top, there with the highest values. So they want to pull the electrons towards themselves the most, and the species at the top left is going to be the thing that wants to be reduced the most, which actually, if we thought about it in terms of oxidizing agents or reducing agents, if this is the most likely to get reduced, is it a reducing agent or an oxidizing agent? So because it's gaining electrons, this thing here, acidified manganate, is our best oxidizing agent in this table, top left. And Mg2 plus would be our worst oxidizing agent because it's a negative number. It really doesn't want to do oxidation. Be reduced. It really wants to go backwards. It doesn't really want to act as an oxidizing agent and gain electrons. It's minus 2.83. It really doesn't want to do it. So that would be our worst oxidizing agent. Over on this side, this would be our thing that most wants to get oxidized and therefore is our best reducing agent. And this thing at the top, Mn2 plus, would be our worst reducing agent. It really does not want to give away electrons. It wants to go from left to right and gain them. It doesn't want to go backwards. This is called an electrochemical series and provides chemists with lots of information, puts these in order. So let's just have a little bit of a recap of some things we might know. So how do metals generally react? So if I said to you, tell me about a reaction of sodium or magnesium, what happens to the metal in that reaction? And we know that metals react by losing electrons to form positive ions. So they lose their outer shell electrons to form positive ions. Now if they're losing electrons, they're undergoing oxidation, and the more likely they are to be oxidized, the more reactive they are. So we know that potassium is more reactive than sodium because potassium wants to lose its electrons more readily, and so the reactive metals undergo this losing of electrons more easily. If they are the things that are going to want to lose electrons the most, and remember this series above is about a list of gaining electrons, the one at the bottom is going to be the one that wants to lose electrons the most. So the most reactive metal will have the most negative, so we're looking at our magnesium there with minus 2.83, the most negative value. And most reactive metals are good. It was our best reducing agent. So the more negative the electrode potential, the greater the tendency for the species on which side of the equation to lose electrons and be oxidized. So which one loses electrons? Is it the thing on the left or the thing on the right? So the thing on the left gains them to become the thing on the right. So the thing on the right hand side of the equation loses them to become oxidized. So that was metals. Why don't we flip and have a look at non-metals? So non-metals like chlorine and bromine react by gaining electrons to become negative ions, so they are undergoing reduction because they're gaining. The most reactive non-metals, therefore, are the ones that gain electrons the most easily. So if we go back up to our series, which thing gained electrons the best? Well, it was a list of reduction, the most positive being the one that gained electrons the best. So they have the most positive values. And the most reactive non-metals are therefore the good oxidizers. Remember I labelled the top left the best oxidizing agent. And the more positive the electropotential, the greater the tendency for the species that is on the left to gain those electrons and be reduced. So as a chemist, I would be able to use this to decide what to use as my oxidizing or reducing agent based on its electrode potentials. So let's put that into practice by having a go at a question. So we're using the electrochemical series on the previous page to find our strongest reducing agent. So the strongest reducing agent, definition of reducing agent, is an electron donor. Who is more likely to give up electrons? So we want to find a species that is giving up electrons. So in our series, remember that they're written as reduction, so the things on the left are gaining and the things on the right are losing, donating. And the more positive the number, the more it gains the electrons, and the more negative the number, the more it wants to lose them. So go back to page 13 and see if you can pick out the strongest reducing agent. So there we go, we would have picked magnesium because it was on the right hand side, so it was going to donate electrons, that made it a reducing agent. To be the best reducing agent, it needed to have the most negative electrode potential. So see if you can find the strongest oxidizing agent and explain your choice. There we go. Now one thing to note there is it's not just manganate alone, it's the manganate and the acid. That's the name of both chemicals on the left hand side. Acidified potassium manganate, we might have described it as. So then we've got our question 2, which says zinc and copper are both transition metals. Which is the most reactive metal? And use the values to explain your answer. So if we go back, so out of zinc, which if we have a look, zinc is here, and copper, which one of those metals is the most reactive? So have a read through about what makes a metal reactive and see if you can answer that question. So there we go, zinc was the more reactive because it was more negative in its electrode potential, so it was more able to lose electrons and therefore form positive ions. Right, so question 3a, I don't want you to actually think about electrode potentials at all. I want you to go back to your understanding of group 7 and describe and explain the relative reactivities of group 7 elements, bromine and chlorine. So what we learned in group 7 is that chlorine is more reactive because it has less shells and less shielding. The nuclear attraction from the protons in the nucleus, therefore, is felt more strongly by electrons, so it's able to attract electrons more and form negative ions, and that means it's more reactive. Now look at the electrochemical series. Is your answer supported by the electrochemical series? Now if you look, you might have to go to the bigger electrochemical series that you've got in your study pack, which shows you chlorine and bromine, and it is supported because for non-metals, remember we want to gain electrons, so we need the most positive value. Cl2 has a more positive standard electrode potential value, so undergoes reduction, gains electrons, which is how it reacts more readily. That's just a little video looking at the electrochemical series and what we can understand from looking at the data.